All right. Okay, good afternoon, folks, and welcome to the last session of the first day of OARC. I'm Shumon Huck, and I'll be introducing the speakers for this session. And up first, we have Willem Torup from NLNet Labs, and he's going to be talking about DNS thought.
Yes, so this is about a hackathon project that I participated in 1.5 years ago, or it started out as a hackathon project. 1.5 years ago, the RIPE NCC organized the DNS measurement hackathon here in Amsterdam. And I participated together with these other people, Andrea Barberi, Petros Kikis, Thierry Lundström, Timuri Taliti and me, we created a tool to look into the capabilities and properties of resolvers on RIPE Atlas. And I've been doing measurements on RIPE Atlas on resolver properties before, and we thought, well, this time we want to have a platform that does structural measurements for capabilities and properties like is the resolver being able to reach authoritative over IPv6, TCP over IPv6? Does it do DNSSEC validation, QNAME minimization, eDNS client subnet, and domain rewriting, that kind of things. And for some of those measurements, you also need the authoritative perspective. So in the course of the hackathon project, Jerry Lundström created the DNS thought daemon that answers certain queries and with information so that the Atlas probes that receive the answer for the query can know what the authoritative saw. And here's an example of a query that is testing for TCP capability and IPv6 capability at the same time. And so it's capable because you get an answer. So it's a combination of a IPv6 only delegation, which is followed, and the DNS thought daemon returned with the TC bit on, so that the resolver had to return on IPv6 TCP. And on top of knowing that it has this capability, the authoritative also echoes the IP address of the resolver reaching the authoritative, so that we can inventory all the different ASs seen at the authoritative in DNS thought. So this number, or this query, which was targeted at quad 9, we can confirm by doing a reverse lookup that it's actually coming from Packet Clearinghouse, which is the operator of quad 9. So this is the RIPE Atlas perspective. There are almost 10,000 probes worldwide, mostly Europe and United States. And they reside in networks, residential networks sometimes other networks. And the assumption is that they are configured as if they were just the ordinary computer in those networks. So what you can see from measurements being done with Atlas probes is all the resolvers that the hosts in those networks are configured with, and also the packets they receive, and it's really an inside look into those networks. And with the DNS thought daemon, we also have the outside perspective at the authoritative side. So one of the interesting properties we can measure, for example, is our Atlas probes using resolvers which have are in the same ASN as they are themselves. In that case, we call it internal resolvers. Or are they configured with resolvers which have an IP address which is in the same ASIN as seen at the authoritative side, which we call external resolvers. And all the others we call forwarding resolvers or forwarders. So we didn't use only DNS thought daemon. We also made use of other measurement or authoritatives that were already providing interesting information, such as this Q-name minimization test from Ralf Dolman. And here are the other measurements that were scheduled during the hackathon. So the hackathon was organized by the RIPE NCC, and therefore they participated in this effort. And so Emil Aben scheduled those measurements for us, for all probes in the RIPE Atlas network, to do the query every hour with no stop time. So it didn't cost us any credits, which is really amazing. And the public measurements, so they can be used by you too. This was the portal that we created 1.5 years ago. It was more or less showing the capabilities and properties of the resolvers at each probe, the location of the probe, etc. And that was a good result at the time. Later, other people I came in contact or became part of the Root Canary project as well. And we took along scaling measurements for all the different algorithms used by DNS keys and all the different DS algorithms, or we made zones for them and scheduled measurements with RIPE Atlas for all the probes to do it forever, for every hour. And this year, 19 July, we also added 2 measurements together with Moritz Müller for the Sentinel records. So the initial portal had gave a display of the capabilities of probes or the resolvers at certain probes, but I thought the more interesting thing to see is how those capabilities developed over time in the last 1.5 years, especially since RIPE Atlas now itself has the facility to tag probes with certain tags indicating certain capabilities they have. So that functionality is now better dealt with within the RIPE Atlas probe itself. And for us, it's more interesting to see development of capabilities over the last 1.5 years. So here you see the distribution of the Atlas probes, of the internal, external, and forwarding resolvers. So that didn't change much. You can see that most resolvers are internal. So the plot is the progression of those properties in the last 1.5 years. The big pie chart is the number of resolvers that have this certain property. And the small pie charts are the probes that have a resolver with a certain capability, or in this case, the number of probes that have an internal resolver, number of probes that have a forwarding resolver and external resolver, so they can overlap. And that is sometimes interesting. So above this plot, there's the web page where you can look or see this plot. And on the web page, it's possible to see all kinds of plots for all the different capabilities for resolvers. But it's also possible to select or only the resolvers that have a certain capability. So here we see the plot of the resolvers that have only the, or that are seen, let me see. Oh yeah, at the authoritatives. So you see the yellow part arising there, or appearing at April 1st, it's Cloudflare. So this is a plot of only the internal probes that have only internal resolvers configured, or the resolvers that are only internal. You can see from the small pie charts that there are certain probes with internal probes that also have forwarding resolvers or external resolvers. So ASNs seen at the authoritative from internal resolvers are mostly in residential ISPs like Comcast, Deutsche Telekom, the Free SAS, etc. So if we look at the forwarding resolvers, we see a completely different picture at the authoritative. Here you see all the larger public resolvers. 35% Google. There's Quad 9 appearing the 17th of, or the 16th of November. And also Cloudflare clearly makes an entrance on the 1st of April. And if you look at the external resolvers, so the resolvers that have an external IP address configured at the probes, then you almost only see Google, OpenDNS, Cloudflare, and very little of the other public resolvers or smaller resolvers. So one thing you can see with DNS thought is that diversity of resolvers used decreases from internal forwarding to external. Interesting thing to look at is DNSSEC support. This is from the front page, the plot that shows DNSSEC validation. With Atlas, more than half of the probes have DNSSEC validation. So in the next plot, I show you only the resolvers that do DNSSEC validation for the most common algorithm. And you see in the small plots there that 16% of those probes that have a resolver that do validation also have a different resolver that does not do validation. So realistically, although it's more than 50% of probes at RIPE Atlas have a resolver that does DNSSEC validation, it's only 45% that is protected. This is the root key trust anchor sentinel support. So it's a measurement with which you can see which key signing keys, root trust anchors, resolvers have configured. So zooming in, I could see that everybody has the new key signing key. Everyone that supports this new algorithm also has the new key. But the interesting part when you make such a selection is sometimes the bumps. So the sudden bump here got my attention, and if you then scroll up on the same page, you see the seen at the authoritative, and then you can see that somewhere, or at the start of August this year, the Bright House networks started to support this specific algorithm. Now I'm going quickly 2 slides back. So you see this DNSSEC support also has this little bump, right? So that's also interesting. So if you look at the plot for all the ASNs that do DNSSEC validation, you can see what's happening, what's the cause of this bump. And it's actually was Cloudflare that suddenly appeared not to do DNSSEC validation anymore. And here's the plot. Here's the selection of probes that are coming from, or are seen at the authoritative as coming from Cloudflare. And so you actually see that some of those probes using Cloudflare still do DNSSEC validation. So I asked Marek, the developer of the Cloudflare resolver, what was going on. And he said there was an issue with RR6 not being cached, and it only happened to RR6 that expired, and yeah, so that was the case. So looking on the same page, or going down to look at, I noticed in the plot that showed Ghost DS support, which Cloudflare apparently does not have, that there are certain probes that do have Cloudflare resolvers that suddenly have broken Ghost DS support. So then, with DNS OARC, you can look at a page with only the probes that have broken Ghost DS support. And then you can immediately see which probes were causing this problem. And those were all the probes coming from Google. And so I also emailed Alexander Dupé what was the cause of this, and they said, yes, there was an issue. They had a mitigation for other people that used Ghost DS immediately, but they did not have a mitigation for our domains, because they are also part of the root Canary project, and they were used in remediating this issue, helping out in getting rid of this cost issue. So sometimes, you can look at plots that are in use with only certain providers, and then you see this. Let me just put on the next one. This is from the resolvers that do the Ethernet curve 24519 validation. So that was Cloudflare from the beginning. Google from September this year. So on this plot, which shows you the probes that have those resolvers, you can clearly see the non-validating Cloudflare resolvers and the broken DS support at Google, which is nice, I think. So EDNS client subnet, mostly done by Google, OpenDNS, IP-only telecommunications in Sweden. Here I selected only OpenDNS. You can see which EDNS client subnet masks they are sending, just /24/64. And with Google, it's a whole range, and it's also interesting to see in this plot that, for example, in September 2017, they suddenly switched from /24s to /32s. So these numbers are coming from the Google Echo query. And it's not clear from that query whether this mask is for IPv4 or IPv6. So that's improvement for the DNS thought measurement, but it's interesting to see this development of different masks used at Google. Also note that the /64 at the beginning of this year changed suddenly in the /56. Oh, QNAME minimization. Cloudflare does that, so the blue bulb there is Cloudflare. Here's the plot showing EDNS subnet, client subnets done by probes that also do, or resolvers that also do QNAME minimization. So currently, this is almost none, as you would expect from privacy-aware resolvers, but that might change, I've learned today. On the right, you see that probes that have a EDNS client subnet resolver also, for 80% sometimes, do not have it. NX domain rewriting, those are my last plot that I want to show you, is almost only done with internal resolvers. So obviously the big consumer ISP, Deutsche Telekom, and I also make plots to which ASNs they are rewriting the NX domain. So Deutsche Telekom has its own NX domain rewriting service, but British Telecom makes use of Barefruit, etc. That can all be seen in the DNS thought measurement portal. So that's my talk. So I've concentrated on doing processing those measurements And I made just a very rough interface to provide access to the data. So I've spent no time on making it pretty, look pretty, etc. The raw tables generated from the Atlas measurements are there too. It lists also the Atlas measurements involved, but I can tell you it's quite a big piece of data if you want to do that crunching yourself. It's about 7.5 gigabytes a day. Yeah, so it's not we're not doing the capabilities per probe anymore because I think that's better fitted with RIPE Atlas tags, and there's lots to improve. And if you have questions or suggestions, then I can answer them now.
Okay, any questions for Willem?
So Puneet from Google Public DNS. So thank you for doing this. It helped us deal with the DS ghost problem. We had been notified earlier, but the root canary helped us verify the fix went through. That's why we didn't put an override rule for you. And that was basically we are doing another fix, nothing else. We are doing a fix for RFC 4509, and as part of that, we broke the ghost algorithm checking. And the /32 from Google is IPv6.
IPv6.
Yeah.
Okay.
Anyone else? Okay, so let's give a hand to Willem. Thank you.
Okay.
Okay, so our next speaker is Santosh Balakrishnan from AFNIC, right? And he's going to be speaking about DNS in LoRaWAN, and he's going to enlighten us about what LoRaWAN is, I think.
Thank you, Shimon. So my presentation today is about DNS usage in LoRaWAN. LoRa long range is a wireless data communication technology that is used extensively. So to give you an idea of, there are about 50 million devices deployed in 95 countries. And if you see the ecosystem, we have big names like the device manufacturers like ARM, Multitech, to Google Cloud, to Alibaba. There are 500 to 600 companies, which is called a LoRa Alliance, where they create the standard for LoRa. And when we say LoRaWAN, it is LoRa Wide Area Network. Here it's the IoT technology. So we have the RF side, which is the long range, which communicates with physical and MAC layer, and wide area network, where we integrate with the internet. What is it? Okay. So today, the overview of the presentation is that AFNIC, my company, has been working like 10 years on IoT. We are not married to any technology, IoT technology. Our objective is to look at how we can use DNS in IoT. So we had previously worked with the consumer industry, like 5 years, and we developed a standard. We contributed to a standard called ONS. I will talk about it later. Then to appreciate why DNS is used in LoRa, we need to have some background about LoRa infrastructure. I will have 2 or 3 slides on that. And then how DNS is used in current LoRaWAN specifications. So if you see here, DNS has not been used only for fully qualified domain names. It has been used for other purposes in different variants. The second one, EPC, is the electronic product code, is an identifier like the fully qualified domain name, and the naming service that has been developed with contribution by the AFNIC, it is called ONS, Object Naming Service. So it is a variant of DNS, specifically oriented to specific requirements of the GS1, that is the standardization organization is GS1. The application use case is in the consumer industry. We have other type identifiers called object identifier, which is used in, like, I think it is an X509 and all. And the naming mechanism is object resolution system, which is also a variant of DNS. And we have DOI, digital object identifier, and the naming service is handle, which is, at the beginning, we use DNS. So DNS has been used in different variants before also. Now, this is what we have worked with the GS1 organization, where we contributed to a standard called ONS, Object Naming Service. So what is the use case here? At the identifier part, in the place of FQDN, we have EPC, which we see electronic product code, and that is used to identify the products for the consumer industry. So it can be barcode, it can be RFID, anything. So the use case here is that when you scan the barcode, that is converted to a URL, and where you can have, like in the right-hand side, we have extended packaging, where you can have more information about the product other than what you see on the label. And also another use case is like track and trace, where you can have all the instances of a product from the manufacturer to the distributor to the retailer till the end of the product. And all these instances are stored in a database called the discovery services. So to find the discovery service for a particular product, ONS has been used. So all this, when I say has been used, is like only for the standards. So we even now the consumer industry has not used it in an industrialized manner. It is only in standards. So as I know that there are two root servers for ONS, onsepc.com, which is managed by VeriSign, and onsepc.fr, which is managed by Orange, but both are not used by any of them. It has just been in the standardization stage. It is not used industrially. So let's see about LoRa. LoRa stands between the LAN, where you use LAN technologies like Bluetooth, Wi-Fi, NFC, etc., and the cellular. What is the advantage of LoRa? LoRa advantage is that it is cheap, it has long coverage, and what is the inconvenient of LoRa is that you can send like one packet per hour, like in bytes. So it has a market segment where you need to have information not in a higher bandwidth, but in very low bandwidth, like in agriculture, like in smart buildings, etc., and etc. If you see LoRa, why is it cheap? That is one of the biggest advantages of LoRa, is because it uses unlicensed spectrum. You don't buy the spectrum, and then if you put a device, for example, for a flood maintenance system, you put those devices around a river, and this device can stay for like 10 to 15 years of battery life. And to give you an idea, to have a coverage for a country like France, the capex cost is like $3 to $4 million. And and we can have also individual LoRa network, where we can have it in like $500, $600 to have for specific use cases. Then in the urban areas, the coverage is like 1 to 5 kilometers. And in rural areas, it's like 10 to 15 kilometers. So it doesn't have the disadvantages of other wireless technologies, like it has to have routing infrastructure and all. The device communicates directly to the gateway, which acts as an interface between the radio frequency and the internet. So this is the LoRa network topology, where we have the end devices at one end, and there's a gateway in between, which talks both LoRa as well as IP. So the device communicates directly with the gateway, and the gateway orients the packet to a network server and other things on the right side, which is all communication via IP. So here we have network server, app server, and joint server. The network server is the one which receives the data, processes the data, and see where it has to be sent. The app server is where you have the cloud information and all, and the join server is the server which gives you an idea for a purpose called over the air for processing the keys and making encryption and decryption. So there could be cases where all these three different servers will be same, will be one server, or there could be cases where it could be separate. So now the question is, why LoRa Alliance chose DNS? As I said before, since it is cheap, there are a number of private operators that has been used, like in a building, for security, for flood maintenance, for agriculture and all. If you see the case of cellular, there are 3 or 4 public operators in a country, and it might like 400 or 500 operators. So in the case all over the world, in the case of roaming, they can have a database where they can have interactions between these 400 or 500 stakeholders. But in case of LoRa, you have public operators. For example, in France, Obgenius, as Bouygues and Orange are public operators, and you can also have number of private operators. So having, like, for example, 300 to 400 private operators in a country like France and having interaction between them is very difficult. So that's why I think it's not that we had asked them to use DNS, but the specifications already states that the recent specification, LoRa 1.1, already specifies that it uses DNS for 2 use cases. One is over-the-air activation, and another is for roaming. When you say over-the-air activation, is that I will show you maybe. Over-the-air activation is that keys are pre-provisioned between the device and the network server and the application server. So they have to derive these keys, derive a session keys to have encryption, decryption between them. So for that case, we have to have an activation mechanism over the air. So in that case, DNS is used. The next case is roaming. For example, if your device has moved out of your coverage area, right, because all the gateways will receive the information from the devices in their coverage area. So if it moves out of the coverage area and another gateway, which is not the owner of the device, receives this information, what it does is that it has to find out which network server is the owner for this device. For that case, we need DNS. So just to give you an idea how the data is provisioned in the LoRa infrastructure, the device has an identifier, which is called the dev UI, and it also has another identifier, which is called Join EUI, to find out which is the join server corresponding to the device. Then it has 2 keys, network key and application key. The network key is used to encrypt and decrypt between the network server, and the app key is used to encrypt and decrypt between the app server. So these information has to be pre-provisioned earlier in the network server as well as in the application server. So this is a small proof of concept that we did. Actually, at the deployment stage, we didn't see anybody using DNS. They are still using LoRaWAN 1.0, which doesn't have this functionality. So we tested internally. We used a open source LoRa server implementation, and then we added the information corresponding to the join UI in the DNS server, which server corresponds to which join UI, and then we tested it. So I'm not going to detail about other things, other parameters here. So we tested, like, for 2 devices, whether the OT activation is done with the appropriate join server. So for both the devices, it was successful. But LoRa has some limitations. For example, the device sends a join request. Join request is used at the initial, before the handshake, to get the keys and get the device activated. So it sends a join request, and it waits for like 5 seconds. If it doesn't get the response within these 5 seconds, what happens is that it goes to sleep, and it wakes like 1 hour or 2 hours based upon the configuration. So these are the issues wherein the DNS resolution should be done within a specific time frame. So we have just tested internally, but in a large scale, we don't know whether it will work. So now what we see is that once the over-the-air activation is done, there are much more information added to the key, added to the device. Now the device has other parameters like the session keys to encrypt between the network server and the device, and the session keys to encrypt between the device and the app server. But what we are going to focus on is the net ID. The net ID is a unique ID to identify the operator for which the device works. So this information is needed for roaming. So this is how roaming works. Let's say the device has moved out of the coverage of its own gateway. A foreign gateway is receiving the packet header, and it says it is not part of its network server. So it forwards to its network server. The network server is the one which processes the packets. So it says you are not part of my network. So what it should do is that it adds a suffix, a subdomain to the device. For example, LoRaWAN, LoRaAlliance.org or somewhere, and it sends to the DNS. In the DNS, we have information corresponding to the net ID to the operator, which is owner of this device. So the owner of the device will get this information, and it will become the home network server, and the device and the network server, which is actually communicating with the device, will become the forwarding network server. So this is how roaming is done in LoRa. Now this is the LoRa Alliance, LoRa DNS tree, where under the LoRaWAN we have two zones, which is called net IDs for the roaming purposes and Join EUIs for over-the-air activation purposes. So this is still not operationally working. So we are still working with the LoRa Alliance, and maybe in the future these zones will be provisioned to have roaming as well as over-the-air activation by using DNS. So these two use cases which I explained currently, the specification mandates that, and in the future, people who are using LoRa and they want roaming and over-the-air activation, they have to use the DNS. Now, the other use cases that I'm showing here, it is not part of the specs, but there are problems faced by the LoRa ecosystem, which they have complex solutions which could be easily solved by DNS, sorry. So this is one of the use cases. The device identifier, it follows a pattern, which is the IEEE pattern, IEEE EUI 64 pattern. So here, the red part, you have OUI, which is the object unique identifier. Then you have a batch ID, which is in green. Then you have serial number, which is in pink, which differentiates each device. So the problem with them is that, for example, when a manufacturer creates the devices, he creates in different batches. For example, he says 1,000 devices at a time, and he puts all this information into those 1,000 devices. So for all those 1,000 devices, he will add a same join EUI. So that is on the yellow. It is indicated in yellow. So what happens within these 1,000 devices? If somebody buys it, let's say someone A buys 500 devices, another B buys 250 devices, and another C buys another 250 devices. The problem they have is that they have to use the same join server if they provision in the DNS, because the join EUI is the same. So that is an issue identified by the device manufacturers. So how it could be solved? It could be easily solved in the DNS, where if we reverse, the serial number comes to the end, the device identifier for the device as well as the join EUI is reversed and it's concatenated, and we can easily separate the join servers for each company that wants to have it. So this could be easily done by using DNS. The next is that why not use IP as an identifier, which in many IoT technologies, people are looking at how we can use IP as an identifier in the device for communication. The same problem comes with LoRa also. So there is the problem that we find is that the IP header is quite large, which is like 48 bytes, and 6LoWPAN, which is IPv6 over low power personal area networks, they have compressed this IP to like 10 to 12 bytes. But in the LoRa use case, we don't need routing information between these devices because it communicates directly with the gateway. So, but the necessity here is that the device can have application information to be communicated, for example, QAP. So in that case, there's a group in IDF which is called LPWAN group, Low Power Wide Area Network, and they have a draft called SCHC. It is static SCHC. It is called SCHC, Static Context Header Compression, where they say that they could compress those informations with a rule. It's called the compressed residue and a rule ID, and they can compress it to less than 1 byte in bits. So we were seeing that whether we could use that in the LoRa purpose. So what happens is that the compression is done, and the device has some context information. It will have like 3 or 4 context information, and it will compress based on that context information, and it sends that to the gateway. In the IP side, the network server will have number of context information, and based upon the rule ID, it decompresses the information. So we were thinking, why not put this context information over DNS, and based upon the context information, you get decompression and compression. So this is just an idea, it is not implemented. Similarly, there is another problem with the LoRa, where we have to have the keys, the shared secret keys, have to be provisioned manually before. So the problem is that in this ecosystem, there are a number of people. For example, the manufacturers, then we have somebody who buys the device, he is the device owner. Then if he's not technically competent enough, he gives to somebody who is called system integrator. Then there are other people like network operators, joint server operators, app service operators. So how do we share these keys? One of the examples that you see is that you have the keys being printed behind the device. So these are some use cases that happens in LoRa, or you share it on mail. These are different issues that could be solved in another way. So we just have a wild idea where we say that why not use DNS as a trust anchor, where the manufacturer and the network server and the application server have key distribution and key provisioning in a trusted way. So this is just an idea. We are looking at different mechanisms like DNSSEC, DANE, DOT, etc. But this is just a wild idea. So these are the use cases that we think could be used in LoRaWAN, and we are working on it. So that's it. And if you have any questions.
Any questions for Sandosh? Okay, let's show our appreciation. Thank you, Sandosh. All right, and last but certainly not least, we have who I think many people will agree is one of the more entertaining speakers that the OARC crowd has seen. And he's going to be, this is Bert Huber from Power DNS, and he's going to be talking about Hello DNS, which I think is a teaching instrument. So it doesn't sound like too much of an inflammatory subject, but we'll see. All right, welcome, Bert.
You know, I could just rant about DNS over HTTPS for half an hour if you want. I mean, but let's not. So, let's bring my book and my trusty camel. I want to thank Ken from Farsight for shipping us this camel. We're very happy with it. It's in our office. It keeps us honest. You need that kind of thing in your life. Okay, behave. Very good. Okay. Welcome to DNS, or Saving the DNS Camel, with apologies for the OCD people that the OR is not quite centered. There's a long story behind that. I can tell you over beer. Yeah, there we go. So, DNS software, it's pretty dire stuff. We have the glorious open source software. The authors are here. They write good stuff. If they don't write good stuff, we'll let them know. Outside of this world of glorious software, it is dire. It is very bad. If you see what gets shipped in load balancers, in printers, in Netflix sticks, within apps, it is all horrible. I did some investigation on my own lab, or my house as I call it, and I looked into unexplained DNS traffic, just to figure out what devices, what things in my house are doing DNS that cannot be explained. And I found the craziest stuff. I found a TV that was doing non-randomized DNS queries, or at least randomized in a very interesting way. And the ID field was just static, and the source port was, well, very predictable kind of random. Of course, this is only my TV, so it's not that bad. Then I found WhatsApp. And it turned out that WhatsApp, which is used heavily in Europe to communicate, if it doesn't get an answer it likes from the official name server, it will fall back to Google Quad 8. With ID is 1 and port is 53. And so I reported that to the Facebook people, and they were nice and professional about it, and they took like 3 months to fix it. They gave us a bug bounty, which we offered to charity. They doubled it, which is nice. So, see, DNS can be good for things. So we can wonder, why is it so bad? Why do we have set-top boxes? There's a country here in Europe, it's called Switzerland, and they have like 250,000 set-top boxes out there sending out surfail queries. And the amount of traffic coming out of those boxes is so big that it has to be dropped by access list rule. It has to be dropped at the networking level because it's just too much. And also, well, actually PowerDNS can take it, but it skews the statistics. They look weird. So they filter it out so the graphs look neat again. This is the standard. That is what happens out there. Your printer, your proverbial fridge, and your WhatsApp stuff, it doesn't get DNS. Why doesn't it get DNS? Well, of course, these guys writing that stuff, and all guys, they're amateurs. Stupid amateurs, they don't show up to these conferences, they have no clue how DNS works. It's all their fault. This is the prevailing wisdom until like March 2018. And then I went to the IETF in London, and I looked at the amount of DNS stuff that was happening, the standards that were in progress. And I thought, how many pages of DNS are there? How much would you have to read to become a DNS expert? And it turns out this is 2,000 pages. Okay, what does it look like? So I made a viewer and said, let's figure out which DNS, which RFCs describe DNS. Some of them are really core DNS. Others describe stuff you could do with DNS. Then there are informational RFCs, and there are experimental RFCs. There is actually even one RFC that no one knows what it is. It has no status, and so that skewed my graphs a bit. And it turns out that depending on how you count it, there are between 2,000 and 3,000 pages of DNS you have to read. And in graph form, that looks like this. So over the years, we've been writing more and more RFCs, and it's 2 pages a week. So who here is currently typing the 2 pages? Yeah, we have a candidate. So just to visualize it, I went through my books, and I thought, can I find a 3,000-page book? And I found one. The Chemical and Rubber Company Book of Chemistry and Physics. This contains the combined knowledge of chemistry and physics. It has less pages than the DNS RFCs. It seems to be a contradiction. Actually, these okay, you're right. You can haggle a bit. These pages are really thin and they're full of numbers and stuff. But you know, let's rip out half of this book and it's still an evening's read. So, and the thing is, so what can we do to sort of? I mean, this is a problem. I mean, do you actually have to read all those 3,000 pages? It's a question. Well, I looked into that. What sort of minimum set of stuff you need to read? And it turns out that even the most basic questions about DNS, you need like to fall through 3 RFC update cycles to get to the point. So it always ends with 1034, 35, but there are typically 2 or 3 RFCs stacked on top of that to answer any question. The only sort of question that you can find in 1035 is, what port do I use? And even that is no longer true since we now have DNS over HTTPS. So there you go. This is the complexity that goes with it. This is some drafts I wrote down which are currently in progress. And eventually the complexity of DNS is going to be such that it'll break and people don't get it. And I worried about that, and then I called my presentation just, something about the DNS camel that will sort of the last straw that breaks the camel's back. And I think that point is imminent. This could happen any day now. How do we stop this? How do we make sure that this does not explode? Because this graph here has been remarkably steady at 2 pages a week. You cannot see from this graph when the DNSX working group shut down. You cannot see it. It's invisible. Apparently these people just kept on typing. So actually, just funny show of hands. Who here is an author of an RFC? Yeah, we're all guilty. Okay, good to know. So what can we do? Can we sit down and rewrite the RFCs? Can we do a cleanup? Can we once and for all write it down so that we collapse all these layered RFCs into one? And no, we frankly cannot. Because anytime we try to do any kind of effort like this, we get into a big fight over what is a packet and why are we on Earth actually. I wrote my own RFC. I had a huge discussion on what is random. And yeah, Olafur remembers. Yeah, that was a horrible. Olafur, by the way, provided some tremendous guidance to behind the scenes to actually make that RFC happen. But that was necessary. But if we try to do that now, if we sit down, then pretty soon we're back to why are we on Earth and what does Earth mean and whatever. So it's not going to happen. We are dysfunctional that way. It is also very unrewarding work. There's no glory to rewriting an RFC. So it's not easily going to happen. Then there's the question, can we simply scrap RFCs? Are there a few of them where we can say, well, we can live without those? And it turns out, yeah, but it's only like 2 of them. Which out of the sort of 200 ones that applied, yeah, I mean, there's 1%, and no one was reading them anyhow. So the alternatives are, can we explain the current DNS better, or can we please stop writing new ones? So I suggested that, and this led to this wonderful Twitter thread, and I think everyone in this thread is in the room right now. So Gavin noted that Joe Abley found the term camel attack, which is sort of a sneaky way of increasing DNS complexity without being really noticeable. And then I lament and say, yeah, but people keep on writing these new RFCs. Even we, I mean, even PowerDNS keeps writing them. And then noted philosopher Robert Edmonds, he correctly figured out that if you tell people, look, I know it's your job to write standards, but could you please stop it? It's not very viable career advice. I mean, you sit there, yeah, what do you do? Well, I'm trying to improve DNS by, not doing my job. So it's difficult. I mean, if it says on your resume that you are into writing DNS standards, that is, you will get to the office and you will start doing that. So I can understand that it's very difficult to stop writing more RFCs. So there is an alternative to writing new RFCs, that is explain current RFCs better. After my presentation in London, Olafur and Job Snijders, they came to me and said, well, thank you for complaining about DNS. What are you going to do about it? It's a very good point. So I decided to do at least something. So I started a project called Hello DNS, which attempts to sort of provide a nice, clean entry point into the world of DNS. Now, of course, none of you need this. Turns out this is not true. When I was writing this stuff, I found out that there were areas of DNS that I did not understand. So it's actually not just for these my first DNS server people. This could be a good refresher. So what's the goal? Provide a fresh entry point to DNS that helps people solve problems. So imagine you are this person writing this Swiss set-top box, and you're confused about the meaning of a query and a response, and the surfail field. This would be the kind of page where you go, okay, I need to write some kind of DNS software that answers a question. How do I do that? What are the rules of the game? So the goal is write stuff that helps people solve their problems. Richard Stevens, who we still miss, did this for TCP, IP, and Unix. So you had the POSIX standards and the other Unix standards, and they were nigh unreadable. And then Richard Stevens wrote this wonderful book, TCP, IP Illustrated, and the Unix programming environment, in which he said, okay, well, you can read the standards or you can read this book, and this book is a lot nicer. And that's the same goal of Hello DNS. So you have this sort of descriptive language, but there are a ton of footnotes that say, well, you should use port 53, and if you want to know why, that is in 1035. But the goal is also to not be shy. So let's say if you read a really old RFC, it has stuff about all kinds of records that no longer exist. It has 1970s security advice, which we should dismiss. So the goal of the project is also to say, well, don't do this. For example, the older original RFCs, they tell you if you get a UDP response from a different IP address than to which you sent the query, you should accept it, because that's helpful. And they explained because it's a commonly made mistake to return from the wrong address, so that's why you should accept it. A later RFC tells you to please not do that. And that's an example of the stack of RFCs you have to read to do the right thing. Because the first document you read says, well, don't check the IP address, and then the second one says, yeah, do. So I want this to be a collaborative effort because my time is also limited. But it should also be curated, because if anyone that wants to speak their mind on DNS gets their way, it becomes another 2,000-page document. I also really want to add readable and runnable code, because we have done ourselves a massive disservice over the past years by making name servers ridiculously fast. We've been benchmarking these things. I am guilty of this. Everyone here is guilty of it. And everyone at one point needs to get their name server product to do 1 million queries per second and do a presentation about it. If you make your name server do 1 million queries per second, there's a trail of blood running through your code to make that happen. And it's a gory, gory affair. So I worked on DNS Dist last week, which was, by the way, launched in this place 3.5 years ago. And I tried to add some stuff, and I found out we have now 3 ways of sending response packets. And because of the benchmarking efforts. So nothing is simple anymore. So if you would tell someone, do you want to learn about DNS? Well, go read the code of a name server. Well, take a welding mask. It's not an educational thing to do. And this goes for Power DNS, it goes for all, we have all succumbed at one point to saying, okay, we need to make this stuff like completely lock-free, and we have used some obscure locking algorithms. It's not educational material. So this is the first page of Hello DNS. This looks pretty good. It looks like it's sort of finished because all these links are blue and you could click on them. And parts of them actually get you to useful content. So the core of DNS is described. There is stuff for authoritative servers that is pretty good. There is some stuff on the optional elements, but it's like a sort of Christmas tree with not all the balls are in yet. So it looks nice, but it's not there yet. But this is the sort of entry. Cover everything you need to know, so that you know what you need to do. It's written in Markdown and MarkDeep, which is fun because we all like editing stuff on plain text files and not in Word. And it uses MarkDeep, which is a Markdown dialect, which gets you this sort of nice and slightly off-center. Yeah, I know it hurts. I know people here that are dying of this. But at least it's easy to type, okay? And it has version control on it. So it's good. So you can make these nice graphs and diagrams. And it has a thing called Teachable DNS. This is a feature-complete name server that originally fit in 1,000 lines of code, and then I sort of, there were a few more things I want to cram in there. So it went from the 1,000-line authoritative name server to the 2,000-line authoritative name server. But it does really cover all the things. So it has UDP, it has TCP, it has sound transfers, it has name compression, it has eDNS, there's even DNSSEC support as long as someone else does the signing. And it's a very, very clean piece of work. You can read this and sort of learn. And I'll get to this. Do people actually care about this stuff? Do they want to know? I wrote this page in April this year, and these are the weekly visitor numbers. And I still don't get it. 40,000 people decided that they needed to read this page. I think this is an indication of the pent-up demand of people to say, well, I want to know more about DNS, but don't come along with this stuff. I want to know more, but give me a better entry point. So it does appear that there is some need. So where are we? Right now, there are some holes there. So the basics are described, but many pages are still placeholders. Right now, it still gets 500 unique visitors a week. This is okay. The TDNS testing name server works, but we're still sort of struggling how to get DNSSEC out of the way, because I want people to first understand DNS and then understand DNSSEC. And there's some specific work needed. So, for example, stub resolvers. As you know, as we all know apparently, a stub resolver needs to get a complete answer to a question. So if there is a CNAME chain, you need to stuff the whole CNAME chain in there so that the stub resolver gets the actual IP address. It will not iterate for you. Try finding that statement in an RFC somewhere. Because I tried to explain this to someone recently, and I couldn't find it. It's nowhere. So it would be good to... Okay, yeah, no, the suggestion is write a new RFC, but no, I mean, this path has no end. So that actually, the stub resolver part needs a little bit of work, so this is what is expected for you from a stub resolver. This would have solved, for example, the example that Mozilla, the mistake that Mozilla made in their DNS over HTTPS stub resolver. They are themselves now chasing CNAMEs. They're not trusting the stub, they're not being a stub resolver. They find that they need to chase it themselves. And which is an easily made mistake, because I would actually also assume that you would have to do that, except that I once read in one of the RFCs that you shouldn't. But I don't know which one. Resolvers. I don't think we should write a manual how to write a resolver, because it has been done many times. But still, we should write some text that makes it clear how bad of an idea it is to write another resolver, so that maybe they wouldn't. The layout is a bit disparate between different pages. So, Teachable DNS, it is lovely right now. This is a web page which you should read, stilldrinking.org, why programming sucks. This also explains why on the first page the little dash was not in the center. This describes how horrible programming is. And your computer programs get horrible because people use them and have strange requirements for them. So far, no one has had a requirement for TDNS. So it's a super, super clean piece of code. But you should definitely also read this URL. So internals, it is written in modern C++. And you can all hate me for that, maybe. I invite everyone to port the 2,000 lines to Go and to Rust or other more karmic languages, Node.js maybe. I don't know. It's, all kinds of people. But the design is rather clean. And so it has long been observed that there's a remarkable symmetry between reading and writing DNS messages and reading and writing zone file format. So every DNS record has the same layout in the packet as in text. So an MX record has a priority field and a hostname field. It is laid out that way in the packet and in the zone file. That means that you can write a SOA record parser like this, where you say, look, we have these XFR functions and they transfer names to packets and names to zone files, or they read from zone files, or they read from packets. And you can exploit that symmetry by having one description of a SOA record, and these few lines create the code that creates SOA records and parses them from packets, and also writes them in zone files or reads them from zone files. So it's pretty clean stuff. It does another fun thing. If you read 1034 today, it is a remarkable difficult read because it describes a tree-like DNS structure that many people originally ignore. They go like, I don't know of any kind of tree, and zone cut, it's a strange word, I don't quite get that. And, but all of 1034 makes a lot more sense if you really think in terms of the DNS tree, because it has some very nice semantics. And in order to keep the name server under 2,000 lines, we had to use those semantics. So the DNS tree, to find any answers, you start at the top of the tree with the whole domain name, and you go down, and every label you go down has to match, and the rest of the name you have to match becomes shorter and shorter. So you can see that described here. So this describes ns1.ort.ietf.org. So that's really nice. So if you use this tree, the whole DNS algorithm becomes a lot simpler. And then we found out that you can use this very same tree 3 times. You can use the tree when you get a query to find the best zone from which to answer. Once you have found the best zone, you can do the DNS algorithm to find if you have the answer or if you should do a delegation or an annex domain. And then when I was writing the DNS label compression code, I found that I could reuse this tree again to find the best place to do a backwards label for label compression. And I thought, wow, these guys in the 1980s, they were so smart. They designed DNS that you could reuse the same data structure 3 times. And because resources were so limited, they must have, yeah, they probably had to be this efficient. So I asked around, I said, well, was this by design? So I asked Paul Vixie and Paul Mokopetris, and they said, no, it was just an accident. So there go my dreams. So this turns out to be a lucky accident, but it does make for a sort of more teachable name server because I only have one data structure to explain and we use it 3 times. So that is rather nice. So this is the little discoveries you make. So what does it look like? TDNS is actually an API for making packets, parsing packets, or messages actually, and looking them up. And this is a very straightforward API and very clean. This is actually the entire implementation of tdig, which now joins the pantheon of kdig and drill, and everyone has to write one of these apparently. This one is not meant to be functional, but this is the entire source code of tdig, which even does eDNS. So this is, of course, in the dreaded C++. And then I thought, let's also make a C API. Because apparently that's much more karmic to write stuff in C. And this was extremely painful. I really didn't know how hard it is to write C, so I'm in awe of all of you guys that managed to do it, and I'm sort of afraid of what you could achieve in a real language. It's true. I mean, I'm not kidding. I'm really in awe because I spent like 2 days on this, only to get the memory management right. But it is a fun piece. For the last few lines, for example, show how you do an MX record lookup. And if you do this if you use this using the Unix tools like res mk query, or even the wonderful get DNS API, it's like 6 screens of text. So it does sort of work. So there is a C API as well for people that like that. So I found a few things when reading this. As I said, when you work on this project, you learn a few things. We discussed, for example, the out-of-zone glue. VeriSign mentioned this morning that they're going to stop that. The DNS RFC strongly suggests that you do actually perform that kind of lookup. And they even suggest that you follow CNAME, that you chase CNAMEs out of your own zone, and that you even might go out and recurse for them. And now, in 2018, we're like, no, we're not going to chase any CNAMEs out of your zone because no one's going to believe the answers. And we're also not going to do out-of-zone glue. So this is the sort of fun things that come out of writing a fresh name server. So where should it go? It's very difficult to write a small name server and to prevent it from becoming a large name server. 3.5 years ago, I presented DNS dist here, and we asked, do people want this? And they said, yeah, we want it. And but I said, yeah, but we should keep it small, like 10,000 lines of code small. That was some time ago. And also a few more tens of thousands of lines of code. TDNS should really be a teaching name server, but it should be full of best practices. So the goal is that someone that wants to enter the DNS field should sit down with the TDNS name server and read it in one day. And then feel like, hey, I know how you build a name server. And I have seen a lot of best practices. And to make this easier, it would be useful to port TDNS to other languages that more people use. Now, this API is actually sort of fun to use. It's MIT licensed, it's simple. Should anyone be actually using this stuff beyond as a teaching product? I don't know. It is suitable for that, and I have found that when actually using it, I have found some further best practices, or at least I found ways in which the name server was not really working. So if anyone has a need for a simple authoritative name server or a simple DNS API, feel free to use TDNS for that. It will not be, it will not suddenly disappear on you. So, some notes on DNS complexity. It was already bad with the 2,000 or 3,000 pages, and it shows no sign of stopping. So in the past few months, we have big, also technical discussions over DNS, on DNS over HTTPS, where, for example, it was proposed to extend the DNS message size to more than 65 kilobytes. Or, in fact, it was said, well, we have not found anywhere in the DNS RFCs where it limits the DNS message size to 65 kilobytes, so we are thinking like 2 megabytes. And it turns out that if we had done that, all the DNS software in the world would have to be audited to see, well, can it actually do larger messages or not? That would have created like person years of work around the world. But it was just as an aside, people said, yeah, we're lifting, just to make it clear, you can now get 2 megabyte DNS messages. Okay. This is easy to say from behind your conference table, but it's rather hard to type in. So apparently right now we already have super complex DNS, and everyone is still super enthusiastic about making it more complex. Now, if I ask any of you, do you feel personally, do you think you will be working on making DNS more complex? Then individually everyone says, no, I will not do that. But collectively the new drafts keep appearing. So my request really is, please help me with the Hello DNS project. Because we get better DNS quality if new entrants to the field actually have something to read that helps them. So it is good for all of us. It means that we have to have less workarounds in our resolvers and other places, and we have to deal with less pain. But the other thing is, if you want to contribute to DNS, which many of us want, you can do so by writing more drafts in the hope that it will become better. You can also help by making DNS more accessible in the hopes that software will get better. And the wonderful thing is, as long as you're working on Hello DNS and writing text, you are not writing new drafts. So please join in. It is very easy to contribute to Hello DNS because it's all on GitHub. GitHub actually has a wonderful markdown editor. So you can edit from GitHub any page you don't like, and feel free to send in pull requests. And I will work on them and to make sure that we continue to be a brief document, and so not everyone's hobby can fit in. But I really need help because I'm willing to curate it. I'm willing to type parts that I'm good at, but it also needs a section on parts of DNSSEC that I'm frankly not very good at. So it really does need help. So if at any point you are bored or you feel like, should I write a new RFC? Then maybe head to GitHub and work a bit on Hello DNS. One final note, Job Snijders from several of the BGP IETF working groups said that they demand reference implementations for things. which in DNS land we've been sort of, they have not been demanding. If you need two reference implementations of your new DNS idea, implementing your idea in TDNS is a lot simpler than implementing it in an actual large-scale million QPS name server. So you can, if someone within the IETF ever becomes wise and says, we will not proceed with standards documents unless we have two interoperable implementations, TDNS might be your friend to make that happen. And I think, really, that is it. I could continue talking, but I stand between you and beer. So I think I'll leave it at this. So thank you for your attention, and please help. Thanks.
Questions? Okay.
Yeah, thank you for this lovely talk. Matthijs Mekking, DNS OARC. I'm wondering, can you split up the numbers of how many pages RFC it is, how many is actually text, and how many is boilerplate?
Yeah, so I saw this question coming. And so I did do that exercise, and it does help. It does help. There is a sort of hardcore of 1,600 pages that does not go away. And you can trim, you can say, okay, we're going to strip the boilerplate, and it's going to be 1,400 pages. But then I have 5 more RFCs where I can say, well, all of these RFCs actually also speak about DNS, so we should maybe include those as well. So for any bit of boilerplate you remove, I have 5 more RFCs to compensate. It really is bad. It really is bad.
I'm just wondering, indeed, because there's a lot of references and the introductory ITF legal blah 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 things there. Okay, 1,400 to 1,600.
It's bigger than the C++ book.
Not a question. You mentioned that you looked into your lab, your house, and see what traffic is going on. I was wondering, what did you use for that?
Actually, so there's a fun story. In March, I did this presentation, and I was really fired up about it, so I started TCP dump on my house. And I left it running for a solid 6 months, because I forgot about it. And then I found it again, and it was full of gold. So it was just TCP dump and forget about it.
Wow, you have some very nice storage.
No, actually, my house does tens of thousands of DNS queries per day, so it's not that bad. Yeah, the GDPR is an issue. I asked my wife if she was okay with it. And, it's not her that's watching the questionable sites, I can tell you.
Yeah, so maybe I heard about SCDN Labs Valleybox, which has a spin protocol, which might be nice in this case because it's a sort of a visualization thing that can show you inside what DNS traffic is actually going on in your home network. So I thought maybe you would be using that.
I'll take a look, but for now it was just a forgotten TCP dump. But I'll take a look.
And yeah, I actually read one of those hits on your, I went to the site and read it, and I think it's a very good effort, especially for teaching things. When I joined the field here, it was indeed quite looking and searching, and luckily there's very great people here that can point you to the right direction as well. So first of all, I think finding the right people is a good thing. Don't be shy there. But having an entry point is very good. I think it's also very good material for educational purposes. I had written up some comments, initial comments, but I didn't have any cycles. I hope to get them soon to get back to there, so I expect the contributions. TDNS. It surprised me, it was like 1,000 lines you said, and there's 2,000 pages, and you said it was feature complete. I was like, oh, that's amazing. Yeah,
but I mean, I host a domain name on it. Let me put it that way.
Yeah, I'm not so sure about TDNS. I think for teaching purposes it would be good, but the thing that's popping in my mind is like if every developer going to look there, I'm afraid that we are losing the code diversity, which is a very beneficial thing in this community, that we're not all making the same mistakes. So yeah.
I see the risk but I mean, people are going to copy paste. I mean, but I think they're doing that already.
Well, I certainly know people that don't. But that said, I'm going to contribute. I think this might be a nice entry point, and maybe you can write a new RFC out of it.
Thank you for your contribution, in any case.
We're going to go to that mic.
Yeah, all right, thanks. This is Aaron again. Oh, sorry. So I have one feedback, one question to you, and one question to the audience. So that is a really great project. So, you know, I would really read it and try to implement it. So one feedback that I want to give is the DNSSEC part, you know, please don't include it by default. So, you know, it could be an extended chapter, but, you know, from, like I do this job for a couple of years now. I haven't implemented my DNS server yet. I want to do it, but for learning purposes, I will do that. So nobody actually wants me to implement one. So anyway, so the extended chapter will be really good. Like if I want to go for it, I will go for it and read the code. So that's one thing. And the second thing is that, yeah, RFCs are really boring to read, like to be honest. I don't know if it's fun to write, but it's boring to read.
No.
So okay, so this project can actually help people to correctly implement DNS servers, right? I have a question to the audience. What I propose is, has anybody used SSL lab tests for your personal project to check the, you know, the certificate level and, you know, all of those? It gives you, yeah, it gives you A, B. If you see an A, you're okay. If you see B, it actually explains you, you know, why it is that way and how you can actually do it to correct the error. And it actually links a Mozilla link, and so you can actually copy and paste the Nginx configuration, whatever. So what I would like to see is something like that. It's like a TDNS checker or something. I have my own implementation. Check it, see, hey man, you're actually doing the case insensitivity wrong. Here is the part of the documentation. Go there, learn it, fix it.
Yeah. So I'm looking around, but several people have written these kinds of things already. Yeah, so I will not, I think it has been done.
Okay, then.
And also, actually these, but it is good. But some failures, some errors are tricky to spot remotely. So,
okay.
But
that's all right, but at
yeah.
least like as a teaching purposes, I would like to see this is what you did wrong, this is how you can fix it. So,
no.
Yeah. That's all I wanted to ask.
Okay.
Thank you.
Thank you.
I think we're going to go to Giovanni next.
Giovanni, SIDN Labs. Thanks a lot for your presentation, Bert, and I want to say thank you very much for the hours you're putting in that. I think the hours you're putting there, for every hour you put in there, you're saving 10 or 20 hours of other people in other companies. So thanks a lot for that.
It's like exactly the other way around if you write an RFC.
Yeah, that's correct. Yeah. And I wish there was something like that when I started with DNS. So just thank you. And I think it reminds me a bit of the story of Minix as well with Andrew Trenenbaum. I mean, he started with it. Yours is open source.
Yeah,
so
it's a sort of similar concept.
Yeah, thanks.
Okay, thank you.
Hi, Bert.
Hello, Oliver.
Yes, this is great. I was reminded when you were talking that, yes, I asked somebody I work with whether he wanted to write another resolver. And he said, no, that's a task you give to people you hate. And want them to commit suicide.
Yeah, I think so. Well done.
But then I was going to come up here and rant and rave about these people who are clueless and writing RFCs, new ones, and internet drafts. But I decided to check, how many do I have in the pipeline at the moment? So I stopped with that comment. But yes, the protocol has to evolve, or the users of the protocol evolve. So yes, there are going to be new internet drafts. There are some of the other things that people are doing, which is increasing complexity and increasing totally new things. And those are the ones we should be pushing back on. Getting rid of old stuff is absolutely what it has to happen. And yes, keep doing this. And the only thing I'm going to ask you to do, work on your search engine optimization so people actually find this when they type this into Google DNS. Learn DNS, this should be the first thing that pops up on Google, DuckDuck, and all of the other search engines.
Yeah, it's a good point, because I don't actually know where these 500 visitors a week come from. That's somewhat of a mystery.
All of these young kids that I see interacting,
sitting at home,
they all just type it into a browser, search term,
yeah.
And if they don't find it on the first page, they never find it.
Let's see, whatever. That's a good point.
Andre, so I have a checker for if your implementation is correct. I am it, and I just can say no.
I think it is never going to be good.
No, really, but if you have an urge to write a new DNS server, it might be a good idea to contribute to what you did, to debug. Same as with RFC. Instead of writing a new DNS server, please contribute to teaching DNS or Hello DNS. Just don't write just yet another DNS server.
Yeah. This is your good point. If you look at the resolver page of Hello DNS, it is really a very short page that says don't do it. But I agree.
Been there, done that.
But sadly, I think there will always be someone, even a stub resolver. The people that say, I wrote my own stub resolver in the WhatsApp client, they had to write their own mini name server. So somehow I think there will always be people that feel the need to write a new name server. Of course, I also did that 3 times. So.
Yeah, just a quick observation, yeah.
Okay.
Just a very, very quick observation. Jim Reith here. Code complexity, I think, is another big issue. While you were talking about it, I did a little checking. The entire source tree for BSD 4.4 is slightly smaller than the source tree for bind 913, and that's excluding the OpenSSL library. I wonder if something's gone wrong.
I wonder that too. Thank you.
Okay, thank you, Bert. I'm going to wrap up very quickly because, well, it's nearly 6 p.m. and we have a completion of the rollover to celebrate at the social. So, first of all, I'm just going to acknowledge our sponsors once again, to thank VeriSign for being both our 2018 premium patron and a contributor sponsor for this workshop. RIPE NCC is deluxe sponsor for the good activity for this workshop. Comcast, Spamhaus Detect, and Power DNS as associate sponsors. SIDN as our other contributor sponsor. SIDN will be doing a $200 gift voucher for survey results. We will be opening the surveys up tomorrow. Just a couple of quick things. Lightning talks, we still have room for 1 or 2 lightning talks. Please submit them to submissions by 10:30 tomorrow. Likewise, if you want to take part in the PGP signing session, again, send your keys to Matt by 10:30 tomorrow. Social event, you should have registered by now. Ray, do you want to pull up the slide for the social event? So, the boat will leave at 6:30, which means that if all 150 of you show up at the dock at 6:30, it's not going to go. So if you can try and pack yourselves up quickly and get to the dock by 6:15, that would be really helpful. Please remember your badges for the social by whichever way you're getting there. And if you're not getting the boat or you miss the boat, get the metro to Central Station. And then the ferry is free. It takes about half an hour. That's it for today. We restart at 9 a.m. sharp tomorrow. Thank you, everyone. Oh, yeah. Okay, Ray, can you find...
Test. Brilliant. The TTL of the KSK has officially expired. It's 6 o'clock right now.